All right, very good. Thank you so much for the introduction and to the organizers for including me in the program. My name is Stefan Bucher. I'm not a macroeconomist. My research is at the intersection of the computational and the behavioral. But you all made me miss macroeconomics. So this may be a little different, but hopefully there are some methodological contents that will be interesting to some of you, and I'm happy to talk about that more afterwards. I will be talking about a research agenda of mine that's been going on for quite a while that I think of as an algorithmic choice architecture. And this is joint work with Peter Diane. I don't think the clicker is working. Am I going to have to do without, or is there...
Have to do it once.
Let's see if that is going to figure that out. Still no clicker. Oh, well. So I think all of us can relate to information overload, right? Which is the idea that there's just a lot more information available to us than we can process. And that's the case in many choice situations as well. Now, to a behavioral economist, we think a lot about how we can mitigate information overload. And what I want to propose today is an approach that I think of as algorithmic information filtering. And this idea of filtering information is not entirely novel, of course, as Herbert Simon had already envisioned something like that, like anything in life, Herbert Simon has already done it. He had stated that the real design problem is not to provide more information to people, but to design intelligent information filtering systems. And being a pioneer of both bounded rationality and artificial intelligence, what he's suggesting here amounts to combining the two gainfully. So to build intelligent systems that can help boundedly rational decision makers make better choices. And this vision arguably has, at least in part, been realized in the sense that many of our consideration and information sets nowadays are generated algorithmically by recommender systems and so on that are ever more technologically sophisticated. But sophisticated as they may be, many of these systems don't have behavioral foundations. And that can result in problems. For example, recommender systems that fail to take into account the fact that many of our choices are boundedly rational, meaning some of them are mistakes. They misreveal our preferences and then make recommendations that are not relevant to our actual preferences. So what I want to think about today is how we can combine some of these machine learning methods with behavioral foundations to address exactly that problem. And the research question that I'll be addressing specifically today is how a sender can filter information algorithmically to maximize the utility that results from a boundedly rational receiver's choices. So we don't have a lot of time today, so I hope you'll forgive me for introducing the model by way of this silly cartoon where we see a consumer, Bob, who visits this candy store, where he has choices between these jars of candies that contain different numbers of different types of candies. We can stylize Bob's choice problem here as choosing one of these rows, which are choice alternatives that are characterized by different numbers of different candies, which are our attributes displayed in the columns here. And we can assume, for instance, although that's not necessary, that Bob has linear preferences, meaning that each type of candy has associated with it a particular value. Now, the problem that I study is to introduce a second agent that I'm calling Alice. And what Alice does is to observe Bob's full information menu and to present him with a personalized, custom filtered menu YT, either to nudge him towards more desirable choices if she's benevolent, or to persuade him for her own benefit. So what Alice can do for the purpose of today's talk is to just simply select a subset of the attributes that are on the menu. In this example, she selected to display only the blue and green ones, hiding, for instance, the red attribute, because that's irrelevant for the choice since it's not differentiating across the choice alternatives. Now, which information is most valuable in attaining Alice's goal? That depends on Bob's preferences, whatever the receiver is trying to maximize, as well as on his cognitive constraints, by which I mean essentially anything that may prevent him from effectively maximizing. And the difficulty is that we're assuming that Alice does not have access to Bob's preferences. So but instead she has to infer the preferences as well as the cognitive constraints by learning through repeated interaction from the receiver's choices about the preferences. In order to make some progress on this problem, we first of all need a model of irrational choice behavior. And that's one of the main contributions of the paper, which is to introduce a novel theory of multi-attribute choice that is based on rational inattention, that we can then use to characterize exactly which attributes should be disclosed to the receiver, given the receiver's preferences. But then I want to go beyond and think about the case in which the sender does not have access to the receiver preferences and instead has to learn from repeated interaction to tailor information to the revealed preferences. And that will be done using online reinforcement learning. But first, let's specify the receiver's problem in a bit more detail, which is that in each time period, the receiver chooses from a menu, which is simply a matrix like the one we've seen, where rows correspond to choice alternatives. And the key assumption is that the receiver is so-called rationally inattentive. And what that means, in case you're not familiar, is simply that even though the full information menu XT is available in principle, it is not directly accessible to the receiver. Rather, the receiver has a prior belief over the possible states of the world, the possible menus, and can then endogenously acquire a costly signal on the state of the world to base update their belief. Following the rational inattention literature, the cost of that signal is modeled in an information theoretic manner as being linear in the mutual information between the signal and its realization. And as is by now well known in that literature, there's an equivalent formulation of that problem in terms of the receiver choosing a so-called state contingent stochastic choice rule, which is simply the conditional probability, conditional on the filtered state of choosing any choice alternative A. And they're choosing this stochastic choice rule so as to maximize expected utility, which depends on the utility of the chosen action from the menu, parameterized by some preference vector W. And from that expected utility, we're subtracting the information cost, that's the bounded rationality part, which is linear in the mutual information at a marginal cost of kappa per bit of information. For reasons I'm not going to go into, this somewhat innocuous looking problem is actually quite hard, and so we'll be assuming that the receiver is not forward looking and not strategically sophisticated. The sender problem, that's the dynamic part of the model. The sender problem is to choose an information filter, which is a matrix, in our case, consisting of 0 and 1s, that simply selects which subset of attributes is available to the receiver. So the information filter is this matrix F, whose transpose we can use to right multiply the full information state, and this will deliver us the filtered menu, just like we've seen in the example before. And the sender problem will be to dynamically solve this problem of choosing filters that are effective in terms of inducing the desired behavioral outcomes. Now, the key assumption here is that the sender does not observe the receiver's type, which consists of their preferences and their information cost, but rather infers them from observing the receiver choices, so they maintain a belief over the receiver type. And the sender's utility may or may not be aligned with the receiver's, and they may or may not internalize the receiver's information cost. So to summarize, the timing within each period of this model is that first the sender observes the realization of the full information menu X, but not the receiver's type. The sender then chooses this information filter under their prior belief about the receiver type. The receiver knows their type as well as the information filter, but not the state of the world. Instead, they choose the stochastic choice rule given their prior belief. An action is realized from that stochastic choice rule, and the receiver receives the gross utility net of the information costs, whereupon the sender observes the receiver's choice and receives utility that is evaluated under their utility function, which may or may not internalize the receiver's information cost. So before we get to the part that will interest you most, I think the dynamic part, we need to solve the receiver problem. And I will just build a little bit of intuition by walking you through a trivial example, which features 2 alternatives and 2 attributes, a red and a blue one. And we'll assume for simplicity that the receiver has linear preferences over those. So utility is simply a weighted sum over those attributes. We also have to make an assumption on the receiver's belief about the state of the world. And since the state of the world is given by these matrices, where the rows are choice alternatives and the columns are attributes, this will be a matrix distribution, in this case, a matrix Gaussian distribution, for example, where the row is the only variable that will interest us, which is the covariance across the different attributes. Now, when solving the receiver's problem, we have to think about the three situations that the sender can put them in. Either the sender gives them access to both attributes, or only to the first, or only to the second attribute. As a consequence of a theorem that I will show you later, it turns out that we can specify the stochastic choice rule that solves the receiver's rational inattention problem in analytically closed form by writing down log odds of this form, which is essentially just a logit, according to which the propensity of choosing an alternative A depends on the difference in the first attribute weighted by the preference weight on that first attribute divided by the marginal cost of information, and then similarly for the second attribute. Now, things are more interesting in the case in which the receiver has access only to the first attribute. Now, of course, they can condition their behavior only on that first attribute, but they still care about the second attribute, and so they can rely on the cross-attribute covariance row to infer something about the unobservable second attribute from the observable first attribute. So with this solution to the rational inattention problem in place, we can now think about the sender problem, which is to choose a welfare maximizing information filter. And I'll first show you how this looks for the case in which the sender does know the receiver's preferences. We can do so in an example where our attributes are a hotel rating and the proximity to the beach of that hotel, both of which we care about equally and which happen to be positively correlated. And as it turns out, we can very nicely specify the optimal policy. So that's the welfare maximizing information filter choice of the sender, knowing the receiver type. And that, of course, is a function of the state. The state space I'm plotting here, a collapsed version thereof would be a difference in the hotel rating across choice alternatives on the x-axis, and the difference across the beach proximity across the difference in beach proximity across the choice alternatives on the y-axis. And the colors correspond to the welfare maximizing filter choice. So purple means reveal both attributes, red means reveal only the red attribute. As it turns out, this information policy can be characterized nicely using these hyperplanes. And in this example, at least, generally it is best to give access to the receiver to only the more decisive attribute. Even in points of the state space like this one, in which both attributes point towards the same choice alternative. And I don't have much time to go into the details of why this is the case, but just to convey a little bit of economic intuition, it turns out that these attributes can be viewed as informational substitutes, in the sense that hiding the rating information from the receiver will induce them to substitute for that by attending more to the beach proximity. And the sender can rely on this kind of channel. Now, the example that I've just shown you is a consequence of this theorem that we're proving, which gives us a analytical closed form solution to this multi-attribute rational inattention problem, which is a contribution to the rational inattention literature, because generally these problems have to be solved using the Blehut-Arimoto algorithm from information theory. I'm not going into details, but you can see it's essentially a multinomial logit form. So how much time do I have? I'm at sort of 8-10 minutes. Brilliant. Plenty of time. Then I can still show you a little bit more of the theorem. But essentially, you've captured the idea already. The key assumption here is that the receiver's prior belief is in a row exchangeable distribution, and the conditional choice probabilities then take this multinomial logit form with the expected utility resulting from an action. Okay, so now we have solved the sender problem for the case in which they know the receiver type, and now I want to think about the case in which they have to infer that over the repeated interaction, which leaves us with a dynamic problem, and more specifically a partially observable Markov decision process, whose Spellman equation I'm writing down here. So the sender observes the full information state X, and they maintain a belief, which is our belief MVP, And their problem is to choose an information filter F so as to maximize instantaneous utility, which depends on the utility resulting from the receiver's choice of an action, perhaps minus information costs. And then they're taking expected utility under the stochastic choice rule that solves the receiver's rational inattention problem. And then on top of that, they also have to think about the discounted expected continuation value, which notably depends on their posterior belief about the receiver type that they can form by base updating upon observing the receiver take an action A, using once again as a likelihood function the solution to the receiver's rational inattention problem. And so for the macro folks among you, you can think of this partial observability a bit like a Kalman filter, except that here the signal is not endogenous, but it's not exogenous, but it's actually the sender who gets to choose the noisy observation by choosing these different information filters. So they have to internalize what they will learn from making these choices. These problems are hard, and so we're resorting to online reinforcement learning to solve them. And I just want to give you a little bit of a flavor of how the solution looks like in a simple simulation in which we can see a sender who has a belief that is uniform over just 2 points. They know that the receiver values one attribute at 2/3 and the other one at 1/3. They just don't know which is which. And so what I'm plotting here is the sender's belief as a function of time periods of repeated interaction. And since the belief here only has 2 points, a sufficient statistic is the accuracy of the belief, which is simply the probability of the true receiver type, which is up there and under the sender's belief. And we can see that this starts around 50%. And then over the course of repeated interaction, the sender can update their belief. Can go into the right direction, can go in the wrong direction, but eventually the belief converges to the true receiver type, which means that the sender has succeeded in this revealed preference exercise. What we actually care about, though, is the algorithm's performance. And one standard way to look at this, which I won't have to explain to you, is cumulative mean regret, which is essentially the welfare loss relative to the first best in which the sender would know the receiver type. And that's the counterfactual against which we're comparing. And so we can plot this mean regret cumulatively over repeated interaction for the naive, unfiltered, full information benchmark, and then compare the algorithmically filtered information benchmark. And we see that it achieves lower regret, meaning higher receiver welfare in this case. And we can also see that in the algorithmically filtered case, regret stops accumulating after effect after a while, which indicates that the sender has succeeded in learning the optimal information policy. Sorry. Yes.
I got lost.
Sorry.
I have a question on the previous slide, actually. What program were you using to update these beliefs?
POMDP algorithms. Oh, this is an Monte Carlo tree search with particle filtering.
So it was like a library that you just found the algorithm from, or you implemented that, or?
Yeah, there's libraries, and I extended them with the.
The next one, I don't know what filtered and unfiltered are. Sorry, I don't understand.
Oh, I'm sorry. Yes, it doesn't mean much at all. Filtered just means what I've been talking about over the course of the last 12 minutes, and unfiltered simply means the sender is not restricting the information that's presented to the receiver. So the naive action of not doing anything.
So the optimal filtering, right? Or just. You say filter, this is what you mean.
Well, the algorithmic approximation to the optimal filtering, but we don't know the optimal benchmark, or at least I'm not showing it here.
Using the algorithm.
Yes, correct, exactly. So that's all nice and good that this works in theory, but of course, ultimately what we want to know is whether this actually works in human behavior. And so that's why I've been implementing behavioral experiments using exactly this stylized handy choice task, where participants are endowed with linear preferences over these different attributes. Importantly, those are unbeknownst to the algorithm. So we're just telling people to make these choices. They're incentivized according to these preferences, which the algorithm does not have access to. And I think the video here does not seem to be working, but what's happening is that the algorithm observes users' choices and just has to decide trial by trial which information is to be displayed on the next trial. Turns out that people's choice behavior is described very well by the solution to this rational inattention model, which is actually just a discrete choice model. Much like in conditional logic, we can obtain estimates for the preference weight on the different attributes and recover the incentivized preferences nicely. So that's just a sanity check for the model of the boundedly rational receiver's choice behavior. But more interestingly, we can then look at the welfare that results under two compared conditions. So what I'm looking at here is subject's choice accuracy, which is their probability of choosing the argmax on each trial. And we can compare this under the algorithmically filtered information, which is our algorithm, and then the unfiltered information, which once again is the naive benchmark of just showing all of the information on each trial. And in this example, we see that filtering information raised subjects' accuracy by around 7 percentage points and reduced their regret by 1/3. And what's important to know is that this accuracy increase is attained by removing information. So that's sort of the behavioral effect of that. We can also look at this dynamically. Once again, comparing the filtered with the unfiltered information, we see that, of course, they start off in a similar regime, but very quickly, subjects' choice accuracy under the filtered information raises above the unfiltered benchmark as the algorithm learns to provide only the most relevant information. And with that, let me conclude by saying that we think of this as a sort of principled algorithmic approach to information design and choice architecture. What I like about it is that it's non-paternalistic in the sense that it allows us to explicitly optimize for the revealed consumer welfare instead of having to make any assumptions about it. It's of course personalizable and uses efficient online experimentation similar to multi-armed bandit testing. We've built this rational inattention model of multi-attribute choice, which has an analytical solution giving rise to a discrete choice model with some interesting attentional details that I'm happy to talk about. And then we've used reinforcement learning to tailor information to the revealed receiver preferences. And with that, I will stop here. Thank you.
Take one quick question.
This sparse filter is a functional form restriction that you could imagine generalizing. If they were completely unrestricted, would they just solve the rational inattention problem for the agent, or would they do something else? Assuming that they learn the preferences, would they convert to just solving it?
Well, if they know the preference, they can basically just make a recommendation, and
right.
Receiver should just pay that. So only if there's remaining uncertainty about receiver preferences with the sender, more information that is so the sender, of course, is solving in a sense the receiver rational inattention problem. They know how the solution will look like. But the sender has extra information that they can use to guide the attentional choice of the receiver. That's really what they're doing. They're restricting the information structures among which the receiver can choose, because they know the state and they can use that to guide them towards looking where it matters. Essentially, that's the idea. So it's sort of, I think of it like a policymaker telling us information on health effects of smoking because they know something we don't, and so they can help us look in the right spot.